So we are about to do our last integration question. So we've looked at two examples of questions where we find area, and we're really finishing integration by looking at two applications, aren't we? Differential equations was one application. Sorry, we're not doing compound interest, that'd be enough, wouldn't it? Differential equations was one application of integration, and area is the other main one. So both of these haven't involved any new integration techniques, they've been applications of. And so I guess, you know, your mind might be turning to, sorry, wrong. I'm going to stop talking and do this, and then I'll start talking again. I can't do two things at once these days. Right, there you go. Okay, so you might be thinking, well, I really ought to make sure I revise integration. And so you've got these two places, haven't you, to look for topic-based revision. So you've got the linked PDF, and you've got the folder that I emailed you last Sunday, and I'm going to try and put a link to this in OneNote. I haven't quite worked out how to do that yet, but there we go. So integration, I wonder where we'll find integration. Okay. So if I open up that Word document, here we are, and scroll down to the pure part of it. So here we go, and I find integration is part of topic 8. And you know, that includes things that I look familiar with, I'm familiar with. So integration as a limit, methods of integration, area under curve, solution of first order differential equations, partial fractions. Note those two are together, which is interesting. We did do some questions like that where we used partial fractions within differential equation questions. So let's look at topic 8. And you've got it in both PDF and Word document. The PDF version, which is opened up here. And so the third area question I want us to do is a question from that document. And I've just realised I've drawn all over it with the last group and then deleted those, so excuse me while I just delete those annotations. Give going away. Right, here we go. So this is the question we're asked to solve. We're asked to find this shaded area. The shaded area is created by this curve, and we know the function of the curve, it's y equals x ln x, and this straight line, which is a normal to the curve, it is perpendicular to the curve. And so the first thing you would have, and we've got the point where they intersect, it's the point EE, so that's not a variable E, that's the actual value E, 2.7-ish. This is a 10-mark question, so we're not actually going to do all of it. The first thing you would do would be to work out the equation of this normal. You do that by differentiating the function, working out the gradient of the function when x is E, and then doing the thing to work out the gradient of the perpendicular line, which also goes through EE, so you can work that out. I'm going to skip that step and tell you the answer to that. The answer is that the straight line has the gradient minus a half x plus 3 over 2e. That really is a 2, I promise you. So that's the equation of this line here. And we're asked to find the area. So what we've got here, we had scenario 1 was areas above and below the axis. Scenario 2 was areas between two curves. This is scenario 3, which is areas caused by intersections of curves, or in this case, a curve and a straight line. So I guess we need to decide how we're going to go about this. Any idea? What do you reckon, Charlie? How could you go about working out this area? What would? So you're talking about working out that area by integrating that curve. Yeah? I like that. Yeah, I already know this value. This is when x is e. I don't know that value there. So we'll have to work out that value. But yeah, that all seems good. So Charlie's very sensibly suggesting integrating the function x ln x, which is our curve, between some value here that we don't know. So I'm going to call it a temporarily. And e, which isn't a variable, e is actually a number. That's good. So, Pat, how can I work out the remaining area?
Could you use Pythagoras?
Well, Pythagoras work out lengths.
Is it a triangle?
It's just a triangle. Yeah, I'm just going to work out the area of a triangle. Yeah. So I already know the height of the triangle because its apex is here at this point EE. So that is E. So the height is E, 2.7ish. What I don't know is the base of the triangle. So I'm not using any clever formula here. I need to work out that value there. So we'll call that B for now. And that value B is when this line hits the x-axis. And I hope you remember something about what happens when something hits the x-axis. So I have got to firstly find out the values of A, which is where this curve crosses the x-axis, and the value of B, which is where this straight line crosses the x-axis. Go on, have a go. See if you can get anywhere with either of those. We haven't started working out areas yet. We're still in the preliminary stage. There's a reminder of my little flashcard that I hope you've all got pinned to your bathroom mirror or fridge or whatever else works for you. Leave things in terms of E, don't try and get decimal answers. So I'm hoping you made y equal to 0 in both cases. This one is just a bit of algebra. 8 fractions. So I get 3e. So Lily, how long is the base of my triangle? 2e, yeah. So it's, so my base is 2e, my height is e, and I know the area of a triangle is base times height divided by 2. That's all good. Here it's a bit like we had one of these yesterday, didn't we? If it's a quadratic and we want to know when it equals 0, we factorise it. Well, here we go. Consider it factorised. So this will equal 0 when that equals 0. Already knew about that one. Look, it crosses the x-axis at 0. And also when this equals 0. And if I want to rescue the x from the ln, I know I need to e both sides. And anything to the power of 0 is 1. So that gives me So I'm integrating between 1 and e, and I'm working out the area of that triangle, and then I'm going to add those two answers together. So we need to integrate. This is integration by parts. I haven't brought my formula books with me, so let me remind you of what it says on page 7 of the formula book if you haven't got yours. If you want to integrate using integration by parts, it's equal to uv minus the integral of v du by dx, and that's after you've put things in windows. You put things here and here, u and dv by dx. That should make sure that's du by dx. See if you can integrate that. Got to be careful where you put things, because I know how to differentiate ln x. I don't know how to integrate ln x. Well, I do, but I have to use integration by parts to do it, so I'm going to be sensible where I put the x and where I put the ln x. Normally I always put x top left, but in this case we did come across one of this before. Got to put ln x up there. I'm just choosing to write x squared over 2 times ln x is a half x squared. Ln x could write it as over 2. And similarly, when I integrate x over 2, I get x squared divided by 4, because I have to divide by 2, and I've already got divided by 2, which I'm choosing to write as a quarter. And just be sensible at how you use your calculator. You should be able to do a lot of this without a calculator. Remember, the ln of 0 is 1. Sorry, the ln of 1 is 0, and ln of e is just 1. Because that's ln of e to the power of 1. The two cancel each other out.
So let's get the x over 4 again.
So I used integration by parts. Those two multiplied together, which I chose to write like that, minus these two multiplied together integrated.
Okay.
So when I multiply those two together, I get x squared over 2x. X's cancel out, so I just get x over 2, which is x to the power of 1 over 2. To integrate that, increase the power by 1, divide by the new power. It was already divided by 2, so
Yeah, okay, cool.
by all means go on and work out the area of the triangle as well and see if you can add them all together. You could work out the area of the triangle by integrating that between E and 3E. You'd be crazy, but you could. You get the same answer. Okay, so I get, this is my integration answer. Again, I could write that as x squared over 2 and x squared over 4, just chosen to write it like this. When I substitute in e, that's e squared, ln of e is 1, so you just get a half of e squared, and that's a quarter of e squared, so I know together that just gives me a quarter of e squared. And when I make x equal to 1, ln of 1 is 0, so that disappears, and I just get minus a quarter of 1 squared, minus a quarter. So altogether there, I get a quarter of e squared plus a quarter. Over here, I get e squared. So if I add together my two answers, a quarter of e squared plus a whole e squared is 1 1/4 e squared plus a quarter, final answer. And these areas where you've got, and it's often a straight line in a curve, meeting, it is nearly always about breaking it into two areas, or sometimes even more than two, using the intersection points as the break. Okay, integration done. And I do encourage you to seek some practice. There's a mixed exercise at the end of the integration chapter in the book. I've shown you the integration questions from the folder I've shared, and there's integration questions in the linked PDF as well. And while we're talking about questions, paper 1 in the brown paper envelope set, question 14, was one of the ones I said not to do, but actually you can now do that because it's part A is an integration by substitution, and part B is a differential equation question. So that's one that you could have a go at, and you'd be very welcome to come along with me and help me. Actually, today I haven't been taken for cover period 5, so I'm around period 5. I have got some marking to do, but I'm very happy for you to come and sit in here if you wanted somewhere quiet to work. I know sometimes the common room is not quiet. I can't think what else you'd want to do on a Friday last lesson on a sunny day, but you know, there you go. You'd be very welcome if you need somewhere to go. Right. We're moving on to something which, as I promised yesterday, is just a little bit easier. Because we've learnt a lot of techniques that allow us to solve problems Sometimes those are solving equations. Sometimes those are problems which relate to graphs. And those techniques, they are many and varied. The ones we've looked at recently, where we're looking at differentiation integration, they fall under the sort of banner of calculus, but we've also got other methods for solving cubic equations and quadratic equations and all sorts of things like that. But every now and then we get an equation we can't solve. We are stumped. And in those situations we need something which is a little bit more prehistoric, a bit more basic. Example number 1. The trapezium rule we did last week, where we can't work out an area by integrating because we just don't know how to integrate the function, so we split it up into trapeziums. So that is an example of what we now move on to. The umbrella term for these techniques are numerical methods. Numerical methods. And we've already done one numerical method, the trapezium rule. The numerical methods that are left are all to do with finding roots. And the root of something, well, there are 2 situations we find it. It might be we're dealing with an equation where the root is the value of our missing letter, let's call it x, the value of x that makes it equal to 0. So, x squared plus 3x plus 2 equals 0. The roots of that equation are x equals -1 and x equals -2. They are the roots. And if we're dealing with a graph, a function, y equals x squared minus 4, the roots are the place where the graph crosses the x-axis. And of course that's not 2 different things, is it? Because to work out where the graph crosses the x-axis, we just make that equal to 0. So it's actually the same thing. But finding roots crops up in 2 different places. Solving equations and sketching functions. So let's look at an example of a problem that actually we can solve, but it gives us a chance to demonstrate the numerical methods in a nice, easy context. So here is the first example. And you'll find this on page 274 if you wanted to look in your books. So this is a graph. So we're looking at this situation. And this graph clearly has 3 roots on the graph. And we have techniques for finding those roots. We have algebraic techniques, but we're going to use numeric techniques to help us in this example. Specifically, we are attracted towards this root here by the question. The question says, right, there's clearly a root between 2 and 3. How do I explain there's a root between 2 and 3? Well, there is the graph crosses the x-axis between 2 and 3. Not rocket science, is it? It goes on though and says, okay, show that actually if we zoomed in, there'd be another root here between 1.4 and 1.5. Now, we know that one's between 1 and 2. How do we show it's between 1.4 and 1.5? Well, here's what we do. If I make x equal to 1.4, and we use that notation, don't we, for that? If 1.4 is before the root, then that's going to be positive, isn't it? And if I make x equal to 1.5, If that's after the root, then that's going to give me a negative answer. The fact that there's been a sign change between those two values, between the answer to this and the answer to this, indicates that somewhere between those two values it must have equaled 0. Now there are some functions for which that's not true, is it? So for example, the graph 1 over x. If I substituted in x is -1, I would get a negative answer, and if I substitute in x is 1, I get a positive answer, but that doesn't mean there's a root in between those two values. So it only works for some graphs, and that's why these questions often use a graph as well. This one there clearly is a root. So can I get you to substitute 1.4 and 1.5 into that function? And I think it is worth being a little bit verbose. Still use your calculator to do it, but I would, in my method, I would sort of, write it out something like this. I would still start by doing 1.4 arrow x, type that function in, press equals, go up, change the 1.4 to 1.5. I don't want to be doing any substitution manually, but I'm just sort of showing my method clearly. So part A, we'd just be expected to say, well, there's a root between 2 and 3 because the graph crosses the x-axis between 2 and 3. Now we are trying to zero in a little bit on that root. If this sounds familiar, it is. We've done this a few years ago. Well, I think we did. I don't know whether it was one of the things that we hadn't done by the time. I think we'd done it. But of course, I think it's 2 years to the day since I stood before you and wept at the prospect of, well, not you, I knew I was going to see you all. I'm seeing some of them again. Where are the 2 years going? So I'm hoping you get a positive answer and a negative answer. And we're not worried about the exact value of the answer. I'd almost certainly do the dot 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 notation that I often use. But the key thing now, and we're in a bit of a coffee shop dance situation here, is how we state what we found. So I would say that the sign change indicates there is a root between x equals 1.4 and x equals 1.5. And that's one of those things, a bit like with hypothesis testing, where you've just got to do the dance. You've got to say it in the right way. The root is where that algebra equals 0. So by finding one place where it's worth a little bit more than 0, one place where it's worth a little bit less than 0, we are zeroing in on what it actually is. And actually, sign change, that's as far as we get. That's as far as we get. So we can use this idea of sign change, and of course it's not always positive to negative. There's two values here where it goes from negative to positive. So it's just the change of sign. It's not necessarily the order of the sign. Okay, now that's all quite easy. So let's look at a slightly harder example. So in this case, we're starting by sketching a couple of curves. All right. And of course, we're lucky. We can use our calculators for it if we can't remember what those two graphs look like. Both of those are pretty standard graphs that we should know how to sketch, but have a go. And then you've got to see what your sketch has to do with this equation. This is the equation that we're interested in the roots of. So we're trying to work out, you've got to work out what the relationship between the sketch that you've just drawn and that equation is. So Jodie, could you put into words why what we've drawn here shows that this equation only has one solution? So they only cross once, these two lines only cross once, and well done. And how does that relate to what we've got here? Well, yeah, what they've done is they've said, let's find this point. This point is where the two lines cross, so we'll make, they're both written as y equals, so we'll make one equal to the other. And then they have taken the 1 over x away and asked, when does it equal 0? So the reason that the graph shows that this only has one root is that, as Jodie quite rightly pointed out, the graphs only cross once. So this equation only has one solution. I'm not using the word root because remember the root is where an equation equals 0. So if you rearrange it, this equation has one root. And in order for sign change to work, sign change must have an equals 0 equation. Sign change must have equals 0. So quickly whack in 1.7 and 1.8 and then have a think about the next bit. What's the next bit about? Hopefully 1.7 and 1.8 will demonstrate that the root lies between those two values. Notice how they word it slightly differently. So they, rather than saying between x is 1.7, x is 1.8, they use inequalities, which you can use if you want. And we don't have the extra lines because we know it's not 1.7. 1.7 doesn't make it equal 0, and 1.8 doesn't make it equal 0. Now the last bit is the important bit in terms of how this question is different, because we're still trying to find this root. We know it's between 1.7 and 1.8. They then say show that it's 1.763 to 3 decimal places. So how can we use sign change to demonstrate that? It's not 1.764. And it's not 1.765, sorry, 762. It's 1.763 they're telling us, and we have to show that. Any idea what values I could substitute in for sign change? Well, it takes us back to GCSE again. 1.763 is going to be somewhere between 1.7625 and 1.765. We know 1.7635 is going to round up, but everything less than that would round down. So if I can prove that there's a sign change between here and here, I'm proving that the root lies somewhere in that interval, and every number in that interval rounds to 1.763. So that's how I answer this. I use the upper and lower bounds of 1.763 three decimal places and show that there's a sign change. Now, I've already done my verbose thing once, so I'm not going to bother this time because the number's so big. I'm just going to put f of 1.7625 equals, and write what it equals with dot dot dot, and 1.7635 equals. Hopefully there's a sign change in between. Same function, we're just substituting in more accurate values. So the fact that there is a sign change in between those two values means that the actual value of this root, they're calling it alpha, but don't be confused by that, is somewhere in this interval. And every value in that interval, if I rounded it to three decimal places, would be 1.763. So that's the answer to three decimal places. Just one to try, page 276, question 2. You convinced?
Well, when you put in the actual value, it's not 0.
No, the actual answer, when you put in 1.763.
Yeah.
Yeah, that's because the answer isn't 1.763, but the actual answer when you round it to three decimal places would be 1.763. So yeah, we're dealing, normally with numerical methods, we're dealing with equations where the roots aren't nice round values. So it could even be an irrational number, it could be a number that goes on forever.
Yeah.
So yeah, so yeah, that won't give you 0, but the actual answer is somewhere hiding here, and if we rounded it to three decimal places, that's what we'd get. Yeah, no, good question. notice yes another notation in question 2 where they just put those two numbers in brackets. So there's any number way to do it.
Sounds like he's had a real run, doesn't it? I'm not, you know, I've got the, it hasn't tested it, and it hasn't, that sounds worse than this stuff. It's afraid of what it's doing, really. Remember those days?
Did you say that the fact it's a x cubed line means that it would root through this?
Well, I mean, we do sort of know what it looks like, don't we? But no, all they're expecting you to do is to substitute in 1.8, substitute in 1.9, and show that one of them's positive, one of them's negative. That's all. That's all. And again, my point about some graphs don't have roots. We know what cubics look like, so we know this one will have roots somewhere. It's not one of those ones like 1 over x.
Yeah, so you don't have to state that.
No. Oh, right, I see. No, you don't. No, you don't. So hopefully you did f of 1.8, f of 1.9 showed there was a sign change. But then the key bit is the two values for part B were 1.8635 and 1.8645. Again, sign change implies there's a root between those two values. So this is sign change. But of course we can only use sign change if we're given the clue. So show that it's between 1.8 and 1.9. How do we know that it's between 1.8 and 1.9? Where have they got that information from? Well, that's where the second technique that we will learn comes in, which we'll do on Tuesday. Now, I'm not setting you homework. I'm hoping that you're spending time working through the revision questions. You certainly had plenty of questions from me. I mean, if people want to do questions and I mark them, that's fine, but please don't use the absence of homework as an excuse to do nothing. Yeah. I hope you have a very productive but pleasant weekend.